Hello, I'm Sharon Chen, and welcome back to the Lawrence Berkeley National Laboratory's instructional video course on laboratory testing of cookstoves. In this video, we'll discuss how to measure important properties of the water and fuel used in your cookstove tests. Accurate measurements of fuel and water properties are necessary in order to calculate three important categories of cookstove performance metrics required by the ISO: thermal efficiency, gaseous emission factors, and fine particulate emission factors. Broadly speaking, we are interested in measuring properties of fuel and water to determine how much energy was released by the fuel during a cookstove test, and similarly, how much of that energy was absorbed by water in a pot. To measure the energy released by fuel during a test, we need to measure several properties of the fuel. First, we need to know the lower heating value, or LHV, of the fuel we're using. The lower heating value of fuel is the energy released by dry fuel during combustion, not counting for the potential energy contained in water vapor emission products. The lower heating value is measured with a special tool called a bomb calorimeter. Most labs do not have a bomb calorimeter, so it's common to send a sample of your fuel to a dedicated laboratory for testing, or to use tabulated data of typical lower heating values of common fuels. The mass of fuel and char used in your testing should be measured before and after each test using a balance with accuracy and precision of plus or minus 1 gram. These masses will be used later to determine how much energy was in the fuel before the test and how much energy was left in the fuel and char after the test. The lower heating value of a fuel quantifies the energy per dry mass of a fuel, so when testing, we must determine what proportion of our fuel is actually unbound water. This measure allows us to account for some portion of the fuel energy being unavailable to the cooking task, as it is lost to the vaporization of unbound moisture inside the fuel. Unlike the heating values, the moisture content of the fuel should be evaluated or verified for every testing campaign, since it can vary depending on ambient environmental conditions. The moisture content of fuels is measured via the oven dry method. This method compares the mass of fuel before and after unbound water has been evaporated in an oven. Your lab should use a laboratory-grade oven capable of maintaining a stable temperature of approximately 103 degrees Celsius for many hours. To ensure all water has been evaporated, the fuel sample is removed from the oven and weighed every 2 hours until consecutive weighings either do not differ, or rather differ within a predetermined acceptable error. Although the ISO only requires a balance with accuracy of 1 gram and precision of 0.5 grams, we recommend choosing a fuel mass and balance combination such that the balance's accuracy and precision are no more than 1% of the fuel's wet mass. For example, if the wet fuel samples to be dried have a starting mass of 20 grams, we recommend a balance with accuracy and precision of 0.2 grams or better. After the sample stops losing water mass, the fuel is considered completely dry. We can calculate the wet basis moisture content by dividing the mass of unbound water in the sample, determined gravimetrically, by the original moist weight. We note that while the drying procedure is time-consuming and tedious, in most cases it will likely not exceed 24 hours. You may find it impractical to undergo the time-consuming procedure of oven drying fuel samples for every test. In our lab, we use air-dried fuel in a temperature and humidity-controlled environment. Therefore, our air-dried fuel's moisture content does not change significantly from week to week. To easily monitor variation in our fuel's moisture content, we use a handheld electronic moisture meter. Understand that these handheld meters have several limitations. They are substantially less accurate and precise than the oven dry method and should only be used on woody fuels. They are generally only capable of characterizing moisture contents between 5% and 40%, and their accuracy decreases dramatically at higher moisture contents. Therefore, it is not acceptable to use a handheld moisture meter to calculate the moisture content of your fuel, but we can recommend their usefulness to monitor the dryness of fuel that has already been quantified using the oven dry method. If the moisture meter indicates that our stored fuel is deviating in moisture content, we will perform the oven drying method to recalculate the wood's moisture content. In summary, we never use the moisture meter's readings to assess our fuel's true moisture content or to calculate cookstove performance metrics. For that, we only use the oven dry method. However, we find the handheld moisture meter to be a useful tool in assessing whether our lab's fuel is maintaining a consistent moisture content since the last oven dry procedure. In order to determine how much energy was transferred to the pot, the temperature of the water should be monitored with a sensor of accuracy and precision of at least 0.5 degrees Celsius over the expected operating range. We recommend using K-type thermocouples with a high-quality reader. While thermocouples tend to be less accurate than resistive sensors, they are significantly more durable. Regardless of the type of sensor, it should have a probe suitable for immersion in water. The probe should be situated inside the pot of water such that the tip lies a reasonable distance from all walls of the pot and the surface of the water. Consider fashioning a probe holder to secure the probe in place. As an example, we show here our thermocouple probe held in place by a metal holder that rests on the rim of the pot. Now, I will illustrate all of the concepts I have previously discussed by walking through the sequence of fuel and water measurements our lab records during an example test session where we operate a wood-fired, naturally drafted stove to bring 5 kilograms of water from room temperature to a boil. In the hour or so before a testing event, our laboratory staff will begin preparing all testing materials. This includes cleaning and emptying out the stove and pot, readying all instruments for data collection, and gathering together the necessary amounts of wood, water, and fire-starting materials. For these initial weights, we use a balance with a resolution of 0.1 grams that sits to the side of our testing area. Here, we show our laboratory staff weighing out 5 kilograms of water in a bucket, preferably made of a hydrophobic material to prevent water from sticking to the bucket. Weighing out approximately 1 kilogram of Douglas fir wood, and weighing out some fire-starting materials. For this test, we'll use approximately 60 grams of Douglas fir kindling sticks and approximately 15 grams of softwood shavings. Although not shown here, you may find it useful to measure other parameters such as the weight of the pot, the weight of the thermocouple probe and its holder, and the weight of the stove. The fuel we are using today is air-dried Douglas fir. We had previously submitted samples of this wood and its corresponding char for heating value analysis, so all relevant lower heating values are already known and thus do not need to be measured today. We use a pin-type moisture meter to check whether the moisture content of the wood sticks deviates significantly from measurements we took a week ago in similar samples of wood, before performing the oven dry method. Because each measurement with the pin-type meter covers only a small portion of the wood stick, we take a total of 6 measurements, 3 each on 2 randomly chosen sticks. If we do find a significant deviation, we would then seal some samples inside a vapor-tight bag and flag it for oven dry analysis. Once the materials are gathered, we load the fire-starting materials inside the Cookstoves firebox, followed by the pot, the 5 kilograms of water, and the thermocouple probe secured with a holder. We verify that the thermocouple's output, which at this moment represents the initial temperature of the water, is reasonable and logging continuously as appropriate. Finally, we start the fire with a lighter, signaling the start of the test sequence. Over the course of this test, the fire tender strives to feed wood sticks to the fire at a rate that maintains a consistent firepower. This particular testing event will end once the water reaches the boil. We note that at this elevation and with this particular thermocouple probe, boiling water corresponds to 99.5 degrees Celsius. Remember, though, that the thermocouple probe only measures the temperature at one point, not the bulk temperature of the water. Thus, beginning at about 1 degree below boiling, we begin visually monitoring the state of the water. The test ends when there is visual confirmation of a rolling boil, and we note the time and water temperature corresponding to this point. Now that the test has ended, we will need to record the final weights of the water, wood, and char. The following steps must be performed quickly, as with each second that passes, water mass is lost via evaporation, and fuel mass is lost as the fire burns. We insulate the scale from the hot pot and fuel with 2 cinder blocks. We will then proceed to remove the pot of water, the unburned wood, and the char from the stove in order to weigh them on the adjacent scale. We remove the pot of water and weigh it on the adjacent scale. Afterwards, we put out the flames of the fire in preparation for separating the unburned wood from the char. We use sand to quench the flames because with water, there's always the danger of applying too much and thus contaminating the subsequent weight measurements. Once the flames are out, we remove the contents of the firebox and separate any unburned wood from char, guided by visual assessments of texture and color and tactile assessments of density. Both the unburned wood and char are weighed separately. At the end of the test, we make sure to characterize the weight of the empty pot as well as the weight of any unused wood sticks. Together, all of these measurements allow us to properly characterize the initial and final weights of the fuel and water, the initial and final temperature of the water, and the moisture content of the fuel. Using these data, we can calculate important metrics for a cookstove test. To summarize, measuring properties of fuel and water is principally interested in understanding how much energy was released during a cookstove test and how much of that energy was useful energy transferred to the water. To calculate these important metrics, your laboratory will need to accurately measure the following fuel and mass properties discussed in this video: the lower heating value of the fuel and char, the wet mass of starting fuel, the moisture content of the fuel, the mass of unburned fuel and char, the starting and ending mass of water, the starting and ending temperature of water, and any additional potentially helpful metrics such as the mass of your pot or the temperature of the ambient air. Using these fuel and water metrics, you'll be able to calculate important cookstove performance metrics defined by the ISO or other testing protocols. Thanks. I'm Sharon Chen from the Lawrence Berkeley National Lab. Join us for our next instructional video on laboratory testing of cookstoves.